Okay, so I make that 8 o'clock in California and different times around the world. So welcome to this webinar, getting started with Cortex-M software and Arm Development Studio. My name is Ronan Sinnott, and I'm here with my colleague Parina Verma. Hi, Parina.
Hi, Ronan. Thanks for doing this with me. I realize it's midnight in Japan where you're at, so I appreciate you doing this at midnight. I'm Parina. I work with Ronan in the same team. We both work in the tools group in ARM. I'm a solutions architect and help partners with everything, with models, compilers, debuggers, in different phases of their project, ranging from like IP evaluation to software development and performance analysis. Hand it over back to Ronan.
Thanks, Parina. Yeah, as you said, we're both in the same team as solutions architects, so we have quite a global team. I said I'm based actually in Japan, despite my accent, and Parina's over in Massachusetts. So we have a global team presenting this webinar, so bear with us. Hopefully everything will go smoothly. Let's start.
So a heads up before you kick off, Ronan, I thought I'd give everyone a little bit of a heads up. We've tried to keep the live element to the presentation with Ronan and I here through the entire session, but we have pre-recorded bits of these presentation as well. And this is for general reasons. I have a 4-year-old at home, so she might just walk in through the door any minute, which would make for an interesting live webinar. And Ronan being in Japan, it's midnight. So if he does doze off, don't blame him. But with that, I'll hand it back to Ronan.
Yeah, thanks, Parina. Yeah, it's midnight here, and my cat is sitting beside me, wondering why I'm sitting in what he thinks is his bed and what I think is my work chair. So that's going on at the moment. Well, yeah. So this is the latest of our AI Virtual Tech Talk series. You can see we have a few more scheduled every 2 weeks of the next month or so. You can go to our website to see more detail in them and to register for those going forwards. A little bit of housekeeping. All attendees are currently on mute. If you have any questions, we do have a couple of Q&A sessions scheduled through the talk. So if you have any questions as we go through, pop them into the chat box inside the Zoom tool, and we'll pick them up at about halfway and near the end. This is going out live now. It's also going to be recorded, and so some of you may be watching this on the ARM YouTube page. It'll go live in a day or two after this recording. Obviously, Q&A session won't be interactive for those watching then, but please don't hesitate to reach out to us if you do have questions. Our contact info will be on at the end of the deck. So what are we doing here today? Well, we're basically going to talk about developing ML applications with TensorFlow Lite, and then also the ARM Development Studio, the toolchain that ARM provides to help people develop software on the CPUs. The first thing I want to do as part of this is give you all a very, very high level introduction to the Cortex-M family that we're going to be talking about here, the CPUs used in these examples. This is not in any way an in-depth overview of these, just highlighting some of the key points of these processors that's going to be relevant for the information following later on. So what you see here is sort of the complete portfolio of the Cortex-M family, and it goes from the ultra low power Cortex-M0 up to the highest performance Cortex-M7. They adhere to 3 different architectures, ARM v6M, ARM v7M, and ARM v8M. And this essentially defines the instructions that are available to those different CPUs. So the Cortex-M0 and M0 Plus are really very, very small control-based processors. Whilst they can do mathematical calculations, that's not really where they're targeted for. They're probably not the CPUs you'd be looking at for this type of work. Going up the Cortex-M3, M4, and up to the M7, these add more mathematical operations, deeper DSP type instructions that are available to you, up to the highest performance Cortex-M7. And we'll talk about why that's the highest performance in a moment. The V8M cores, those on sort of the right of this slide. So probably the main thing that the ARM V8M architecture adds is a trust zone for Cortex-M. This is a secure state of the processor. You can essentially separate operations into a secure and non-secure world. Now, obviously, that's going to be very important for anything connected, anything where security is going to be key. To be honest, that's an entire other webinar in and of itself. So that's not something we're really going to be focusing on today, but just be aware that that's another feature where that does add. What we will be looking at in the ARM V8M side is the new Cortex-M55 processor. This was launched earlier this year, and it's the first CPU that adds support for our Helium instruction set. Helium is the Cortex-M vector extensions, and this adds a whole set of new instructions, vector mathematics, so single instruction, multiple data type operations to the Cortex-M family for the first time. And what this means is, as you can see on the slide to the left, that as the different CPUs go up in performance for general control and general mathematical operations, with Helium, we get instructions dedicated towards the ML and signal processing type application. So it's a huge order of magnitude improvement over the, for want of a better word, traditional Cortex-M CPUs. So today we'll really be considering the differences between the Cortex-M7 and the Cortex-M55. So the Cortex-M7, as I said, is the highest performance of the Cortex-M families in terms of raw execution throughput. This is mainly due to a 6-stage dual issue pipeline in its architecture, and this results in a core mark score of over 5 core marks per megahertz. So in terms of general throughput, this is the best of the Cortex-M family. It's got a powerful instruction set, including single and double precision floating point options available to it. Conversely, the Cortex-M55 has got a slightly lower throughput. It's only got a 4-stage pipeline built into it, so the core mark score is slightly lower. It's 4.2 core marks per megahertz. However, the addition of this Helium instruction set makes it much better for the type of algorithms that we're going to be using today. Some other extensions, it's also got support for half precision floating point as well, on top of single and double precision. Now, some of these options are technically well, optional to the CPU. So you could, or a silicon vendor could create a Cortex-M55 without the Helium extensions. Now, to be honest, I doubt that is going to happen, at least in the short term. But one thing to be aware of is there are 2 levels of MVE that can be implemented, and this is independent of the floating point option. And this is going to be important as devices come out with Cortex-M55 and you're looking to consider which device is best for your needs. So for example, you can create a Cortex-M55 with floating point hardware, but only where that floating point applies to the traditional scalar ALU. So if MV equals 1 from the silicon point of view, integer only vectorization, but a floating point option available only for the scalar operations. So it's something to be aware of, that not every Cortex-M55 will be exactly the same. From ARM's point of view, we provide the CPU with a number of configuration options, and it's up to the silicon vendors then to implement as needed. Okay, so that's, I said, the high-level introduction to Cortex-M, to the Cortex-M family that I wanted to give you. So now I'll pass over to Parina to talk about developing with TensorFlow code.
So this is the bit that we've pre-recorded, so bear with us for a minute as we set this up.
I've lost the screen.
So while you're figuring that out and setting it up, Ronan, I've just opened the Q&A, and we had a question come in about suggestions or recommendations for resource learning for someone who's new to Arm Cortex-M. That's a great question. So Ronan, do you want to take that one? I can start up. There are a lot of like learning resources available for Cortex-M on our developer site, which is developer.arm.com. But there are detailed documentations for each Cortex-M core. For example, the M7 and the M55 that Ronan referred to. There are technical reference manuals for each of these cores that are also available on the documentation site for ARM. Ronan, do you have more suggestions?
Yeah, that's correct. And actually, one of the links we have near the end talks about a guide for the Helium instruction set and starting to write software for that.
Perfect. Okay, looks like you've sorted the video out. So this is the part that we've pre-recorded where I introduce, the TensorFlow Lite micro frameworks and how we're using that with its tight integration with the CMSIS-NN libraries and porting those example applications that come with these frameworks onto the virtual platforms for Cortex-M7 and M55. So let's kick off that recording at this point.
Thanks, Ronan, for introducing the Cortex-M7 and the Cortex-M55 cores. In the next part of this presentation, I'll cover the process of porting machine learning applications to both the Cortex-M7 and the M55 using TensorFlow Lite frameworks and its tight integration with the CMSIS-NN libraries. So a lot of you might know that TensorFlow is an end-to-end platform that makes it easy for users to build and deploy machine learning models to their target devices. It is targeted towards running the inference in the cloud. TensorFlow Lite is a subset of TensorFlow, which is made suitable for edge devices and is focused on running the inference on the device itself with low latency. Today, TensorFlow Lite powers billions of mobile application installs. TensorFlow Lite for microcontrollers takes the efficiency to another level, targeting extremely low-power devices like the Cortex-M series, and these microcontrollers with just kilobytes of memory. By running machine learning inferences on microcontrollers, developers can now add AI to a vast range of hardware devices, and they're not reliant on network connectivity, which is often subject to bandwidth and power constraints. TensorFlow Lite for microcontrollers can run bare metal. It doesn't require an operating system support or any standard C, C++ libraries. The core runtime itself fits in a very small binary footprint, less than 16 kilobytes. There are several example applications that are included with TensorFlow that show the use of microcontrollers for various tasks, from voice to video to vibration. For the purpose of this talk, we have taken two of those examples, micro speech and magic wand, and ported them to the Cortex-M7 and the M55 systems. Now, these applications, which are available on GitHub in TensorFlow, have support for several development boards, but on this talk, we will be focusing on porting these applications to ARM fixed virtual platforms. Ronan later will introduce what ARM fixed virtual platforms are, but to give you a brief overview, FVPs, or fixed virtual platforms, they're a great way for you to get started with your software development and porting the machine learning workloads to these Arm Cortex-M7 systems without needing an actual physical target board or device. The complete ARM system model is represented by these FVPs, so it's much more than just an instruction set simulator. With the processor, the memory, and other peripherals that are modeled in an entire system in an FVP, you can now port and develop your machine learning software without needing a physical device. So the machine learning applications that are built with the TensorFlow Lite for microcontroller frameworks, they can be built with either the reference kernels in the framework or with the optimized kernels that make use of CMSIS-NN. CMSIS-NN is open sourced. The slides here show you a link to the ARM software GitHub area where you can grab the latest versions of the CMSIS-NN library. It's a collection of efficient neural network kernels that are developed to maximize the performance and minimize the memory footprint of neural networks on Cortex-M processors. It targets the Cortex-M architectures and their support available for the different architectures. The best performance is achieved by really leveraging the SIMD instruction features of the CPU to improve the parallelism that's available in the DSP-capable Cortex-M4, the M7, M33, and the Cortex-M55. It also runs on the earlier versions of the Cortex-M architecture and on the, for example, on Cortex-M0 without the DSP instructions. The preferred entry point to use CMSIS-NN kernels is the TensorFlow Lite micro framework. And the optimized CMSIS-NN kernels, they're compiled into the TensorFlow Lite micro as a library, and then that library is then linked into the final application binary. The flowchart on the left shows you if there is CMSIS-NN support for the operator in your neural network, then the optimized kernel is included in the library. If not, there's always the option to fall back on the reference kernels when the optimization is not available. So that way you can always run a neural network that's supported on TensorFlow Lite Micro on your Cortex-M device, and the optimization can be included and gradually increased based on the support that's available in CMSIS-NN. So here is an overview and a breakdown of the steps that are actually involved in building the TensorFlow Lite micro examples for the Cortex-M7 and the M55 FVPs. You start out with the examples in the TensorFlow repository. Now these applications have been run on several development boards, but we're going to run them on these FVPs, which the framework is not aware about. So you need to add support for the new platforms or the new target systems and provide the information to the framework. This information typically includes things such as the memory map layout of your new target system. The framework also has the ability to generate standalone projects for different development environments such as Embed or Make. In our example, we're using Make to build a standalone project. To include the CMSIS-NN optimized kernels and to use Arm compiler to finally build your binary that will run on your target platform, you need to include certain tags while building the standalone projects, and these tags are called out here, CMSIS-NN and Arm Clang. Finally, you can then run make in your standalone project area, and this will compile that AXF or binary, which will run on your FVP, and this runs the machine learning inference on your Cortex-M7 or M55 FVP. Now, to get you started right away, we've created a Docker project in the Arm Tool Solutions repo on GitHub. So these software examples and the flow that I just talked about is all included for you in the Docker project area to start experimenting with right away. In a moment, I'll touch upon the project itself and highlight the main files of interest. But before I go there, I do want to provide a quick overview of one of the examples that Ronan will be demonstrating at the end of the presentation, which is microspeech. So using the Docker project, you can build microspeech or magic wand. Microspeech is an audio detection based example, which is used to detect keywords yes and no on input speech data. So when you run that microspeech example that you've compiled, what that's essentially doing is it runs on the FVP, which is your Cortex-M7 or M55. It loads the trained TF Lite model on that system. It runs some example inputs through the TF Lite model and checks to see if it got the expected outputs. With that said, let's move to the terminal where we can see the Docker project with all the files to build this microspeech example that Ronan will run later on the FVPs. So hopefully you can see my terminal now. We talked about the steps to set up and build the TensorFlow Lite micro apps and run them on the M7 and M55 FVPs, but to make those steps easy to follow and repeatable, we've captured them in this Docker project on GitHub. So the files that you're currently looking at on my terminal are the contents of that Docker project. Before you get building your Docker image, you will need to download Arm Compiler 614 for Linux. This can be done by running the get AC6 script that's included in the project. You will be using Arm Compiler 614 to build the final executable or binary that runs on your FVPs. Version 614 includes the latest support for Cortex-M55 as well. So once you have the compiler, you're now ready to start building the Docker image for your project. There's a script included here, build.ash. As the name indicates, it's used for building the Docker image for your project, and it uses the Docker file that's also included here to build the Docker image. If we inspect the contents of the Docker file, you will see that it contains all the dependencies and the commands that are used to assemble the Docker project, starting with a lot of the dependencies up front. Some of the things that I wanted to touch upon here is this script download tflow SimSys. What this does is it downloads your TensorFlow and the CMSIS repositories that you will need while building your application. It also copies over the contents of the TF Lite micro FVP support directory into the TensorFlow repo. So if we go and see what really is in this directory right here, as I had referred to earlier in the presentation, the frameworks themselves don't have any notion of this FVP platform, so you need to provide the files to the frameworks to provide information around this new target that you're building for. So this folder contains all of those files that you need to provide the frameworks. The name of the target is FVP, so we'll go into that directory. And you can see here that there is a scatter file included. Then there are some core specific initialization files that are included, as well as platform specific initialization files for your new target. Let's quickly look at the contents of the scatter file. So the scatter file is used to specify the memory map of the image to the linker, and it uses this description in the text file to position or place the image components in different areas of the target's memory. So the scatter file that we're looking at here right now matches the memory map layout of the FVP systems that you are going to be running the image on later on. At the scatter file, but in addition to the scatter file, as I mentioned, there are also some core specific initialization files that are included here, and platform-specific initialization files. Now, while running our applications on the FVP, we're retargeting the output to the UART that's available on that fixed virtual platform. So in order to initialize that serial driver for the UART, these files are also included in this folder. There is one other file in this new target folder that I'd like to touch upon for a second, which is the FVP make file. And there's a section here called platform flags where you can look at all of the different switches that are used to compile your target. So if you wanted to change something like the optimization level or any of the compiler flags, you can change them right here. The linker flags for each of those targets are also available in the same file. Okay, so going back to where we were earlier, we had the build script to build the Docker container image, and now there's the run script where you can run that Docker image and start your Docker container. So you simply execute the run.sh script and you're now running in your container. So now in your running container, you just need to run the single script build tf-lite micro test to build your machine learning application that will run on your FVP. There are two arguments that you have to pass to the script. The first one is which target FVP are you building for? So in my case, for example, I'm building for the M55. And which application are you building? So this here is micro speech, but you can also select magic wand. The same script can easily be extended for the other example applications that are in the repository, such as person detection and even the simplest hello world. But when you run this script now, it creates that final binary that can run on your FVP, and here it'll be called micro speech test.
Okay, thanks,
All right.
Bruna.
Thanks, Ronan. I just thought before we switch to the next section, we could take some questions here that have come in live. What do you think?
Yeah, perfect.
Okay, so there's one that's just come in, which says, can you configure helium for neither the integer nor the floating point? So there are basically two ways in which you, with or without the FPU is what you can configure the M55 with. Then on top of that, dependent on whether you've configured the M55 with or without the FPU, you can also decide to include the MVE or the helium functionality. You can also decide whether you want to include just a subset of the integer, or if you want to include the integer and the half precision and the single precision floating point. So there are a few different ways in which you can configure the M55 itself. And all of the available options are also documented in that technical reference manual on our site, if you want to take a look there. Okay, there is another one that's come in. Is it hard to simulate all the custom real-time sensors and displays that we'll be using in the FVP? Would you like to take that one, Ronan?
Sure. Is it hard is always a great question. So the FVP, so the F means fixed, meaning that it is pre-configured as that is. I'm going to talk in a moment a little bit about the fast model technology that is used to build these virtual platforms. And that is a more general tool that can be used to stitch things up the way that your final device will look like, and also create your own components. So with the fixed virtual platforms, as you'll see, it actually has a screen built in as part of it, and it does have some basic I/O, so you can certainly simulate reading and writing to particular sensors or particular peripherals. But for making something more custom, then the general fast models tool would be used.
Thanks, Ronan. So I'm going a little back and forth. I'm checking both the chat and the Q&A because we're getting questions in both those places. There's one that came in the chat window, which says, is the development environment the Kyle environment? So it's a bit of a giveaway into your next section, but if you want to take that.
Probably best to answer that at the end. We're using the Arm Development Studio tool. A lot of what we're going to show you could also be done with Kyle. It's actually the same compiler in both products, but the demonstration that we'll be doing is with Arm Development Studio.
Thanks. I think that's all we have right now. So should we jump into the next section about Arm Development Studio?
Perfect. Hopefully this works better this time. Maybe not. Technology. So we're going to change tack a bit here and talk about the Arm Development Studio, which is the complete toolchain from Arm for all of our processors, including the latest M55 that we talked about earlier. It's a complete toolchain with a compiler, debugger, and even platforms that you can run on out of the box. The compiler, ARM Compiler 6, is built on the LLVM technology, but is developed internally for the best optimization for ARM processors. As I said, it supports the latest CPUs, so we've been generating and optimizing the MVE instructions for well over a year now at the time of recording. We provide these FVPs that have been mentioned a few times. I'll talk about those in a bit more detail in a moment. We have a fully featured multi-core debugger that we can support either these virtual platforms or real silicon, no matter the configuration. So we're seeing a lot of devices with both Cortex-A and Cortex-M CPUs being put alongside each other, and you can debug all of those together through a single debugger. And this can be either in a model or real silicon through one of our JTAG adapters. We also have the Streamlined Performance Analyzer. I'm not going to talk about this in this particular session in much detail. It targets things like Linux applications. It can also be used in a bare metal use case by annotating your code to garner the information needed to generate that report. We might talk about that in another webinar at some point. But to talk about the virtual prototypes, So these are built on the Arm fast models technology, and that probably tells you everything you need to know about what the technology is. So they are models of Arm IP, so the Arm CPUs for the most part, and they execute very, very quickly, typically in the hundreds of megahertz range. So you can run code on these as fast and quite often even faster than you would do on real silicon. The fast models themselves are modular components of all different IP blocks that you would stitch together to build a complete system. And the fixed virtual platforms that we provide are basically ready-made systems built with these building blocks. If you are closer to silicon companies, you may well use these components to actually build up virtual platforms of your silicon designs well in advance of them being made available to the public. These models are developed by Arm as part of our actual CPU and other IP design flow. So actually they pass the same IP validation suites that the actual RTL silicon designs go through. So you know that what you're working with behaves exactly the same way as real silicon and the real IP will behave. So these are an excellent, easily deployable platform for you to use. They're out of the box with the tools. You can run them locally. They're also really good for things like continuous integration because you can automate them to be run. They can be instantiated and test code can be run on them automatically, and you can just get the output on that quickly and easily. So with that being said, let's see the tools being run in reality. Okay, so here I am inside a development studio workspace, as it's termed. The development studio is available in different editions, gold, silver, and bronze, essentially defining which features are available in which edition, which for the most part means which CPUs are supported. And all of the Cortex-M cores are supported in all of the editions. So this happens to be gold, but any of bronze, silver, or gold will work for you. Now, I've got some of the windows set up here. This is not what it looks like by default. I'm just trying to set up everything that I want to show you. So one nice thing that there is a remote systems view. So in fact, when I was building this code, I ran the Docker instantiation that Perina showed you inside AWS instance that was running Ubuntu Linux. So what I can do is actually just set up a SSH access to that instance. I can see the files on there from the Docker. I even have a nice terminal window if I wanted it. And I can, from there, easily just drag and drop the files I wanted into my local workspace here on my local Windows machine. So a nice little sort of bonus feature that you can use to really easily copy things from one machine to another all inside this one environment. Okay, so the look and feel, it's all Eclipse based, so it should be familiar to many of you if you've used Eclipse based IDEs before. I've got some examples set up here already, but let's just create a new debug connection to show you what you're going to do from first principles. So in the debug control tab, we can create a new debug connection, and it gives us three different options. We can do a hardware connection. This is connecting to a real board or an FPGA platform. And this will use something like our dstream JTAG tools. If your target is running Linux, we can do a Linux application debug session through GDB server on the target. But for this case, we're going to use a model connection and connect to the fixed virtual platforms that are provided with Development Studio. So we can give the connection any meaningful name. Let's just call it webinar. And if I search for one of the M7 examples, we can see that we have a fixed virtual platform provided directly with Development Studio. the name here, MPS2, Cortex-M7. So MPS2 is an FPGA platform that we provide that allows you to build and extend IP around the core from a hardware point of view. So the base subsystem is the same in this model as it is in that platform. So it allows you to easily migrate code from the virtual platform to real hardware. A perfect use case for that. But for now, we're just going to think of the model use case. So select that model. And then the next thing I ask you is what you want to do with that model. So we see that we have this model and it has a Cortex-M7 core within it. Now on some of the more advanced systems that mean multi-core, and you'll see all of the CPUs listed down here. This is just a single Cortex-M7, so that's fine. In our files view, we want to load the micro speech example from the Cortex-M7. So it's a file there. And then in our debugger pane, we can specify that we want to debug from the main function. So the initialization code we're not going to worry about in this particular case. We can specify some scripts. We'll probably talk about scripts a little bit later in the talk, but we have essentially a native GDB-like language as well as a Python-based scripting that you can perform. The scripts are basically the time that they are executed. So the top one here runs as soon as you connect. Typically, this is used when you're working with real hardware where you need to initialize memory before you can download code to it. It might poke particular registers to do that for you. This other type of script, basically when you're all set up. So it might be setting particular breakpoints or some other data that you want to load to the target, that type of thing. You can also specify commands directly in here if you prefer. Okay, so for this simple first case, that's literally all we want to do. So we've basically said we're connected to this model and this core within this model. We're downloading this code, also the debug symbols. So we'll have source level visibility and we're going to debug from main. So with that, click debug. And the model launches and you can see some of the windows populating in the background. All right, so what do we have here? Well, we see in this disassembly view down here where we currently are. So we're at the symbol main, and we can see the assembler level source that's related to that. You can see if you mouse over any of the instructions, it gets a pop-up explaining what those instructions are. You can disable this if you find it annoying, but I think it's particularly useful if you're new to ARM and you're learning these new Helium instructions that we mentioned to get a nice, quick, easy reference of what those instructions are doing. So we have the low-level disassembly here. In this window up here, we also have a list of all of the different functions in the code, and it's a very easy text-based search that you can locate the function that you care about. And from there, you can either jump to the source or set breakpoints from there. I personally use the functions view a lot when I'm navigating around the code that I want to see. If we look at the source window here, you'll see right now that we don't have any source being shown. The reason for that is because the example was built on the Docker instance that we showed you, but now I'm on this Windows machine, so the path is incorrect to where this source code is. But you can see that a button automatically is here popped up to say, basically tell me where the source is now located, so I can tell it straight away. I've got it copied here locally inside this source folder and in this gen folder here. Now you see the path to this particular source file is really long inside the Docker instance, but actually all we need to do is specify the base path here. So you see the same gen folder, which is basically what I copied from here, and all the further pathing from here will automatically be resolved. So we can click OK. And there you go, it's found the original source file here on my local machine. And because we've done that low-level gen path, that any other source that we need to find, it'll automatically pick that up as is needed. So we can look at all of the high-level features of the code here. So we can see the source. We can scroll through it as we want. We can find here the, for example, the tensor arena being created. So if I just set a breakpoint at the instruction just after that and run to there. Forgive me, I've got so many windows and panes here open. I recommend getting a nice big screen if you're working with this normally. Forgive me, there's some sirens going on behind me. Hope you can hear that. So we have the tensor arena here in our local variables, and I can expand this out and we want to see it. Now you can see this has been defined as being a really big, over 10,000 elements of this. So you probably don't want to expand each one out here. But a nice thing to do would be to just right click here and it says show in memory. And that, sure enough, that opens the memory window at the address of tensor arena, and it's looking at the entire size of the tensor arena array. So basically all of the elements are listed here. It's also automatically set the size to be char based or single byte based on the size of the elements inside tensor arena. So we can set this view as we wish. So for example, set it 8 elements per line, so it's all nicely aligned. Make this a little bit bigger. We can change the format of the data in here if we prefer. So we can make it, for example, all chars, or we can set it to 4-byte hex if that's what we want to do. Whatever makes sense for our analysis. Now, one thing I personally like to do whenever I'm looking at big chunks of data like this, we can open a new memory window. Let me just drag this up alongside it. Again, it's nice to have lots of real estate on the screen when you do this. It'll have a history here of the different settings, so it'll remember actually that we used to have it this way. Let's make it byte size and 8 elements per line as before, so it's exact one-to-one match. And now on one of these windows, doesn't matter which one, we can freeze that view and basically say, okay, here's the original values. If I then work down to some other part down in the code and run through that, we hit a breakpoint there. And not only in this view is it highlighted which values have changed, so we can easily look at it and analyze and see what's happened, but because we have this freeze view here, we can see what the original value was. So when it was all initialized, it looked like this, and now as it's been filled, all of these different elements have come in. And more generally, as you're working through the process of a particular algorithm, you can track how all of these values are set. So a few other ways that you can look at data as you prefer. We have this expressions tab, and this is kind of a general purpose view that you can look at really anything defined inside the debugger. I sometimes use this as a shortcut way of looking at things. So for example, if I enter main, I can immediately see the address that it starts at if I'm trying to analyze the memory from that point of view. I can look at various CPU registers. So it's $or0 will show me the value inside R0, make that hex format. We can see also the register window showing us all of the different CPUs, and you can see obviously that matches that value there. While I'm in the register view, if I make this full screen for a moment, you can see there are very many registers inside these CPUs. So there are this sort of general purpose 16 registers, plus a whole bunch of system control registers, and certainly for doing work involving the low-level setup and initialization, you might want to start looking at some of these registers in a lower level form. If there are a particular set of registers that you want to see, you can create your own subset of them. So just create a particular set of registers, pick whichever ones you want, give it a name and add those registers, and the view automatically sets to just those registers that you want, and you can go back easily to all of the core registers as you see fit. So another nice configurable view to the way you want to see it. Another nice thing that you can do, everything you do in the debugger has also got an equivalent command line. We talked about scripting. So if you prefer to drive the debugger through a command console rather than through the GUI, you can do that just as normally. So for example, we have the xexamine command for those of you familiar with GNU debugging. Even if you're not, if you just press Control Space, some local help pops up telling you how to use that command. So all of the additional flags and options that you would use, as well as some examples down here. So very easy to control the debugger by hand. So if I just say, let's read 100 bytes in hex format from the address of Tensor Arena, and it basically pulls the memory there, and you can see that it compares exactly the same as it is in here in the live data. So Charlie Foxtrot, Delta Foxtrot, etc., etc., etc. So there's all our data. So everything you can do in the GUI, you can also do in the command line. And that makes things easier when you're trying to go forward later on to scripting things, to making sure that you can access everything as you wish. Okay, other views of the debugger, we can see the status of the stack, and we can move down through the stack, and as you do that, so the state of the system reflects as best it can what things were. So we can see whatever variables were defined in that function and up into this function. Again, we're sort of in main here and so on, but we can see and analyze as things go on. Another view inside the variables view. So by default, we don't populate the globals window. The reason for that is because in a real target, these will be living in memory, and we would have to do physical accesses to all of those pieces of data every time we stopped. It maybe doesn't matter so much with a model, but this example does have an awful lot of data. So if you find that the things you're looking for are not automatically listed there, so it says we're not showing zero, or we're showing 0 of the 15 available global variables, just click the add button here, go to globals. We can either add them all like I did there, or you could drill down and just pick particular ones. And again, they're all listed out as before. And we can look at the arrays, so we see huge arrays and all of the values. And then just as before, we can look at them on the command line. We can drag them into the expressions view if that's what we would prefer to do. All of those options are available to you. Okay, so that's the sort of basic debugging features that you can do. I'd like to sort of show you an example that we had that actually I helped to decipher what was happening with one of our examples that was used. Let me just clear some of these windows so you know what's going on. So when I was looking at the magic wand example, I noticed that it was not running correctly. So here's my connection. So this is now the M55. It's now a dual core model, but I'm just connecting to core 0. There are a couple of additional settings here you might notice. This one here basically means execute from address 0, and I said the M55 is an Arm v8 core, so that has the trust zone security. So this one basically disables all of that type of functionality, and I'm enabling MVE in the model. As I said, it's an option. I'm loading the magic wand example from the M55 build and debugging from main. You see I've got my little script here to set that substitute path so it knows where the source is going to be, and I'm basically setting a breakpoint at the exit function so it doesn't just spin there forever. So I load the example. So it's all loaded and I can see everything gets populated. Let me close these for a moment, make it a bit easier to see. And I ran the code and it was just running forever. I noticed that on the terminal of the model it was actually spitting out an error. So when I stopped it, I saw that I was in this hang function all the time. So I guess I could investigate it by looking at what the values here in the registers are, but I actually did it much more easily. So these models also support instruction trace, so essentially a recording of everything that it executes. In this DTSL options button here, DTSL means debug and trace services layer, essentially the API of the model. I can turn on tracing here of that core, and now that's all connected. I can just cheat here. I know exactly where the address is. Set a breakpoint at that hang instruction and run to it, and we've stopped there. If I open the trace window, if I make it full screen here, we have a history of what executed. So there's lots of history of basically the printfs of all of that stuff going onto the screen. So if I go back a few pages in the memory, in the history, quite a few pages maybe. Okay, we eventually get to where the example is, so we can zoom close to it. We can then zoom down to a 1-by-1 instruction and essentially go straight through the code. And here we see exactly what happened. So it was on that floating point vectorizing instruction is where the exception occurred, and that was the cause of the problem. You remember in my earlier slides I said that MVE can be configured for integer only or for integer and floating point, and that's exactly what the problem is in this case here. So if I disconnect the model, go back into my settings here, make MVE equal 2, which is integer and floating point. Okay. Everything loads again. So we have the history of all of the startup code here. If you want to see it, it'll run through. Here's all of our history. and we've gone through. We've got to the exit point, and this time it all passed. Perfect. Okay, we're getting close to the hour. Do we have any questions in the chat, Parina?
Yeah, so we have a few that have come in, Ronan. I did answer one while we were presenting about Embed OS, so hopefully that answered your question. There's another one about Embed OS, Ronan. This one is from Grant, and he mentions the current version of Embed OS has a target for Cortex-M7 FVP, but not the M55 FVP. Any idea when it may be possible to target the M55 FVP with Embed OS?
Off the top of my head, I'm not sure. However, the M7 build should run just fine on the M55. They have the M55 is essentially a superset of the instructions on the M7, so it should run without issue. I'm not sure that the OS would make use of the Helium instruction set itself directly. There may be some little optimizations therein, but in general, the M7 build should just run on the M55, and we can certainly check it offline if there are explicit plans for the M55.
Thanks, Ronan. There is another that's come in, which says, can you provide the links for the GitHub URLs?
Perfect timing. Let me hopefully get back onto here. So is my screen sharing again? Hopefully.
Not quite yet. But while you try that, yeah, I think it's coming back up. Yep, there you go.
Right, okay, so yeah, so perfect timing. So yeah, so for everything that we showed today, so you can get a free 30-day evaluation version of Development Studio. You can download it, and then when you start it up, it'll basically ask you to set up an evaluation license. All of the software that we use today is on our GitHub, which you can see there on that link. One of the earlier questions was around information for Cortex-M and Helium development. That's quite a good link there to get started, and also some programmer's guides there. And don't hesitate to reach out to myself or Parina. That ARM Tool Solutions email address goes to both of us and the rest of our team.
Thanks, Ronan, for getting that one. And also these slides, as Ronan mentioned, will be made available for later viewing if you ever want to go back to any of these links. There's another question that's come in, which is, how are the ARM's NPU, especially the micro NPU like the Ethos U55, supported in this tool or flow? So I can take that one. So there isn't a U55 FVP available today, per se, with Development Studio. We covered the M7 and the M55. But that being said, we do have platforms in a similar, using the similar framework, which is fast models integrated with the host processor, which is the M55, and the micro NPU, the U55, running machine learning frameworks and running inferences on these platforms. They're not openly and freely available today. So I would say if you are interested, definitely reach out to us on that email right there, Arm Tool Solutions, and we will work with our product teams, our machine learning product teams, to make sure we can get you the right access and your license to use those platforms.
Okay.
Okay.
That's probably all we have time for today. So just to summarize, yeah, thank you all for joining and bearing with a couple of minor technical hiccups. We're doing this from about as far away from each other as we could be, so hopefully you were able to deal with a couple of minor little screen hiccups as it went through. We'd invite you all to join our next talk. Our colleagues at Edge Impulse will be talking about efficient ML development. So you can register for that on our website. And as I said, this video will also be available on the ARM YouTube page in a couple of days. So if you're watching it then and you have any questions, don't hesitate to drop us an email and we can follow up with you from there.
Thanks, everyone. We've appreciated your time. And as Ronan said, feel free to reach out to either of us on the email armtoolsolutions@arm.com. And if you get up and running with the Docker project and run into any issues or have any questions at all and start using the FVPs, we're right here. We might be in different parts of the world, but we're very easily accessible in this day and age. So thank you again for your time.
Thank you.